Detailed interpretation of zones that have been deformed either by salt or tectonism can be quite challenging. These heavily reworked zones are quite critical, especially in areas like the North Sea, where that can have a profound impact on both fluid migration as well as containment. The complexity of these intervals usually means that they go underinterpreted, which can actually create multiple uncertainties around both the target and the well path itself. Therefore, we can leverage new technologies like interactive deep learning and take a data-centric approach to obtain a more accurate representation of the seismic facies, separate them out, all in under a day within the Groningen Field. The Groningen Field is located in the shallow waters of the North Sea, as well as onshore the Netherlands. The reservoir is gas-bearing in nature, and it is located within the Upper Rotliegend group, which is Permian age, and is characterized by a four-way closure as well as stratigraphic pinch-outs. The regional seal within the area is the Zechstein Salt, which is immediately overlying it. Finally, the source rocks for the area are from the Nemurian carbonaceous shales as well as the Westphalian coals. To characterize the entire dataset, we took a top-down approach, which meant that we started with the larger features and then used that to then identify some of the smaller, more subtle features. We started by characterizing the salt, and by only labeling less than 1% of the data, in under 1.5 hours, not only were we able to label and train the network, but we were also able to generate the probability cubes and automatically extract the geobodies as well as the top and base surfaces. Masking and validation methods were used to focus the neural network only on the relevant data, but also to avoid overfitting. From this, we were then able to separate out the facies into 4 distinct packages, which were identified both from the well-logged responses, as well as from their distinctive seismic waveform characters. The time it took to label and train the multi-class seismic facies network, as well as generate the probability cubes and associated horizons, took about 10.5 hours. What's critical is that a full 3D manual mapping of these seismic facies can almost be near to impossible. It takes a significant amount of time, and even traditional deep learning methods and seismic waveform-based classification methods can yield maybe noisy and ambiguous results. However, with this method, in under a day, we're able to not only produce a full 3D characterization of these facies, but more importantly, they're supported and backed by well data, and we're able to match those. With interactive deep learning, we're able to successfully identify these zones, and this is critical because now we have a better understanding of pre-drill uncertainties, and we can optimize our well path to ensure success of the program. And the great part, this methodology can be used for any geological or geophysical feature.